Good afternoon. My name is Jayakumar Radhakrishnan. I'll be your chair for this session. We have two talks in this session. The first talk is on some vignettes from quantum computation. The speaker is an old friend of the TIFR family. Ashwin Nayak was a summer student at TIFR Mumbai 3 decades ago. Right now, he's a faculty member, a professor at the University of Waterloo. Ashwin.
Thanks, Jayakumar. It's a pleasure to be here at ICTS-TIFR. In fact, the last time I was in Bangalore, it was also for a workshop that was held under the auspices of ICTS, although it was at the Indian Institute of Science, a bit south of here. This campus was apparently just in the planning stages, and it's really nice to be now in this beautiful campus. So I was charged with the responsibility of giving an overview of the developments in quantum computation, especially the impact of quantum mechanics on computation. It's going to be especially challenging because somehow I have to compress 30 years of work into 30 minutes. And I guess the bigger challenge is that the talk is happening right after a sumptuous meal. So I hope I can keep your attention, but here goes. I'd like to start with some of the history of the field. In fact, some of the prehistory. So this notion of what computation is arose from, in fact, from the study of the foundations of mathematics, in fact, in the logic community, with this thought of whether we could automate somehow the process of proving theorems. Several models of computation were proposed in the 1930s, so evidently after the birth of, in fact, the formalization of quantum mechanics. But nonetheless, none of those different models, recursive functions, lambda calculus, or something closer to the kind of computers we see today, Turing machines, involved the use of quantum mechanics. What was soon realized was that all these methods that were proposed, or models that were proposed, were equivalent in the sense that any function that you could compute in one of the models could be also computed in the other, and vice versa. So this observation led to what is known as the Church-Turing thesis, which encapsulates this idea that not only these models, but any reasonable model of computation was equivalent to one of these, especially, let's say, the Turing machines, in the sense that the set of computable functions remain the same under all these models. Now, much later, in the 60s and 70s, people in communication theories started wondering how they could communicate using optical means. And quantum mechanics came up naturally out there. So people like Gordon, Hellstrom, Hulevo started looking at how much information, so firstly, how you could encode information in quantum states, and how much information you could transmit using such states. An early set of ideas on the use of quantum mechanics in cryptography came from Wiesner, who in conversations with Charles Bennett described a way of designing quantum money that could not be counterfeited, and also gave rise to this idea of oblivious transfer that was discovered much later in computer science. You all have heard of the quantum key expansion scheme by Bennett and Brassard, which was it originated in the 1980s, but finally was published in '84, and as it happens, at a conference that was held in Bangalore. The idea of computation with quantum information stored in quantum states, came about much later, in the 1980s. Benioff noted that ultimately computers that we design and manufacture are also physical objects, and as such ought to be able to be viewed as quantum mechanical systems and model them as well in terms of spins and hamiltonians and such. And at the same time, I believe Yuri Manin in the USSR also had this idea of a quantum computer, and Feynman also mused about computers based on physics. His motivation came from a completely different perspective. He was wondering how well we could simulate quantum systems using computers. And he observed that if we, well, the straightforward method of doing it, which was to basically write down the entire wave function, was going to be extremely exorbitant in cost and in time. And he wondered whether if instead you would use a quantum system directly to do the simulation, you could first, of course, I mean, he thought you could do it better, but also whether you could simulate all quantum systems using such a computer. David Deutsch tried to formalize this. He came up with a formal model and proposed what one can think of as a physical version of this Church-Turing thesis, wherein he formally recognized that a computer is ultimately a physical object, and as such, we would like all models of computation to be capturing the same set of computable functions. And he noticed that for his particular model, this was the case. So he gave this notion of a quantum computer, which computed the same set of functions as you would be able to using, let's say, Turing machines. Nonetheless, he wondered whether this idea of quantum parallelism that's sort of inherent in quantum superpositions could be exploited to do something more. This idea was crystallized more crisply by Bernstein and Vazirani in 1993, who formulated it in terms of what's known as the extended Church-Turing thesis. And this is how they formulated it. Any reasonable model of computation can be simulated efficiently by a probabilistic Turing machine. By that time, the notion of efficient computation had already also been studied, formulated, and a distinction was made between when machines could simulate each other with, well, not too much more resources than they would consume to actually run the original process. And also that the use of randomness could lead to extraordinary savings in time or space or such. So their notion of a reasonable model of computation would also included the notion of efficiency and probabilism. So the question that David Deutsch asked could now be posed as follows. Do quantum Turing machines challenge this extended Church-Turing thesis? And there were early indications by Deutsch and I believe his student Richard Josa, which was further developed by Berthiaume and Brassard, which showed that in certain restricted models, one could show, in fact, exponential advantage over deterministic rather than probabilistic Turing machines. In 1993, Bernstein and Vazirani formalized the notion of Turing machines, put it on, sort of formulated it in rigorous terms, worked out the basics of the complexity theory that follows from such a definition, and succeeded in proving in what's known as again, a restricted, what's known as a relativized model, that there are problems, possibly contrived, that quantum computers could solve efficiently, namely in polynomial time, that no probabilistic Turing machine or probabilistic computer could solve in less than super polynomial time. This was noticed by a cryptographer, Dan Simon, who, like me, when I saw quantum computation for the first time, was highly skeptical of its power and even its possibility. So Simon wanted to show that certain cryptographic problems could not be solved efficiently using quantum computation. But in the process, he discovered a problem that's now known as the Simon problem, wherein a quantum computer gets an exponential advantage, so can solve a problem, the Simon problem, in polynomial time, whereas any probabilistic algorithm would necessarily take exponential time in the length of the input. Turns out that this particular algorithm, the quantum algorithm that he designed, had a feature that Peter Shaw recognized could be used to attack problems like integer factorization and discrete log. Essentially, what was at the heart of the Simon algorithm was a procedure to detect periodicities in certain functions. And the same kind of structure could be, or problems like factoring and discrete log could be formulated in such a way that they exhibited similar periodicity, and this could be picked up by the quantum Fourier transform. The result was an astonishing polynomial time that's an efficient algorithm for a problem like integer factorization and also discrete logs, where people for years thought no such algorithm was possible. The world sat up, and it was suddenly, there was an urgency to sort of look at what quantum computation was all about, whether it was possible to actually build such machines, and what other notions in quantum, well, in computer science, in complexity theory, would be challenged by this new model. So in the rest of the talk, what I'd like to do is basically highlight some of the advances that have been made in the field in the 30 years that followed this discovery by Peter Shaw. In fact, I'll only be talking about things that happened in the last 20 years, given the time that I have. And I apologize in advance for not mentioning things in between. There'll be leaps I'll make where certain works will not be mentioned just because of paucity of time. And unfortunately, I wish I could give credit to everybody that was involved, but won't be possible. So let's start with the first vignette. So this is on formula evaluation. This is the following problem. We have a Boolean formula f. It involves n variables, and the gate set, which is and, or not. It's read once in the sense that in the formula, any one of these n variables occurs only once. So an example is the OR function, the OR of n variables, where there's only one gate and its arity is n, and this function takes value 1 if and only if any one of these n variables is 1. At least one of them should be 1 for this function to be 1. Now, the problem associated with this formula is the following. Let's say you give an instantiation to these n variables. So you give them Boolean values in 0, 1, and ask what the function value is. The complexity measure will be how many variables do we need to evaluate to basically check to be able to compute the value of this function. Now, it's not too difficult to convince yourselves that any randomized algorithm will essentially have to look at all possible n inputs. Because in the worst case, what could happen is that the first input that you pick would be 0, and you would be unlucky in the second trial as well, and so on. And you would be then left with no option but to check all of them. Now, what happens when you allow a quantum algorithm to try to evaluate this function? By a quantum algorithm, we mean one that can read these variables in superposition and also maintain a state of the algorithm that can be evolved under some unitary transformation. Now, if you think about it, this problem is exactly what Grover studied in 1996. He called it the database search problem, but this is nothing but a simple mathematical reformulation of it. If you think of these as n items in a database, the fact that one of them is 1 as indicating which item is marked, then Grover's algorithm finds the marked element in square root n queries to this database. And so the same algorithm gives you a square root n algorithm for evaluating the OR. Let's look at something a bit more interesting. This is an AND/OR tree. It's a tree involving n variables. It's a binary tree. It's a complete binary tree with depth log n. So there are log n levels of gates. And each gate is binary so that it has arity 2. The gates at alternate levels are the same. So let's say you start with an AND gate. The next level has only OR gates, then again AND gates, and so on. At the leaves are these variables. Here I've shown you a depth 4 binary tree with 16 variables. The function that's computed by this formula is what you expect. You basically take the OR of these 2 variables and then do the same with the other 2 lying next to it, then take the AND of the result, and so on. Again, we can ask, how many variables do we need to read in order to evaluate the function? Now, again, n suffices. That's the obvious way to do it. But turns out there's a cleverer algorithm that's randomized. Okay, and it's based on this idea that you don't always need to evaluate every branch of the tree. So for example, if you're at an OR gate and you happen to discover that the left branch evaluates to 1, then you're done. You know the answer to the gate. The answer is just 1. And so you need not evaluate the right subtree of the formula. And that idea, with the use of some randomness, gives rise to an algorithm that computes this function with n to the something like 0.75 checks of variables. What about quantum algorithms? So one can, one might be tempted to try to use Grover search recursively, but it fails quite badly for several reasons. One is that, at each level, you're computing basically the or and of a constant number of variables, and any algorithm that does it will incur, some constant overhead, and these constants will basically multiply over log n levels, and any advantage that you gain would be lost with this overhead. And moreover, the algorithm is, it has some error in it, in the sense that it doesn't always give you a correct answer with certainty. And those errors would accumulate as you evaluate the formula at the different levels. But nonetheless, stunning algorithm was proposed by Fari, Goldstone, and Gutman in 2007 that used completely new ideas that came basically from the theory of scattering. And what they showed in a certain model of continuous quantum computation involving continuous sort of checks of these variables, that order square root n checks suffice. And others later on picked up on this, on the essential ideas within this algorithm, formulated an algorithm in the more standard notion that had been developed, equivalent to the Bernstein-Vazirani model, and showed that you could not only reproduce this behavior, the square root, the quadratic speed up over n behavior for these balanced, full binary tree formulae, but also arbitrary, potentially unbalanced read once formulae. The final algorithm, which was developed by Ben Reichart, has many nice features. One of them is that it gives a new modular technique for designing quantum algorithms. But you might say, well, what's the big deal? After all, you're just getting a polynomial speed up over what was known before, what you could do with randomized computation. Well, here's something that you might not expect. One of the things that this algorithm implies is the following mathematical statement about polynomials. So suppose you have this formula f, and you would like to approximate it with a real polynomial in the variables x1 through xn. Okay, so you view you would like to approximate it in the following sense, that this polynomial should take values at all the possible inputs to this function, so all the 2 to the n inputs to this function that are close to the function value. So if the function value is, let's say, 1, then this polynomial should take values between, let's say, 2/3 and 4/3. Right? And if the function value is 0, then it should take this p of x, polynomial p of x, should take values between negative 1/3 and 1/3. So it's entirely not clear how one would construct such a polynomial ab initio without having knowledge of this particular quantum algorithm. Well, you might say, so what? Why should we care? So here's why. Turns out that once you have such a polynomial, you can develop a classical algorithm for learning what the function f is solely by looking at its values on these many random samples. So let's say somebody is giving you samples x and the value of f at x. For x drawn from some distribution, you don't know what the distribution is. Question is, how many random samples would you need in order to be able to correctly predict the value of f at a different point that is drawn from the same distribution? And the answer is 2 to the square root n, roughly. The naive way of doing this would take exponentially many samples as well as exponential time. And if you think about it, the randomized algorithm would have given you something like 2 to the n to the 0.75. And this here is a super polynomial factor better than that. Okay, so 2 to the square root n is much, much smaller than 2 to the n to the 0.75. So having designed a quantum algorithm, by some magic, we essentially have obtained a classical algorithm that is much more efficient than was known before. And to date, there is no other proof of such, this kind of algorithm even existing. Let's look at another problem. This is a problem from the study of many-body physics. And I'd like to focus on one particular kind of local Hamiltonian. It's a Hamiltonian on the line. So there are, in this we have n particles, n qubits, so these are d-level systems, and they interact with each other pairwise along this line. So there's a term h sub I, a Hamiltonian term h sub I, that specifies the interaction between particle I and I plus 1. There are n such terms, or n minus 1 actually, because there are n minus 1 pairs. We assume that each of them is bounded, so the operator norm is bounded by 1, and the Hamiltonian is given by the sum of these local terms. Standard questions about the local Hamiltonian problem are, well, what is the ground energy? Can we approximate it? And we might get more ambitious, and we might ask for a description of the ground state. Now, in general, like any quantum state on n particles, its description would be exponential in the number of particles, right? So we don't expect this problem either, finding the ground energy, so finding such a special ground state. By the way, for those who are not familiar with this terminology, the ground state is essentially the eigenvector with lowest eigenvalue, and the ground energy is the lowest eigenvalue. So this problem is essentially asking us to compute the lowest eigenvalue of an exponential size matrix. So we don't expect this to be an easy problem, and in fact, it was shown that this problem is at least as hard as the general case where there is no restriction on the geometry and no restriction on the locality of the Hamiltonian terms. So, you could have particles interacting with faraway particles, and even when these interactions are local in the sense that they involve a constant number of particles, it was shown that these, finding or even approximating the ground energy is what's known as QMA hard. You don't need to worry about what that means. If you know what NP is, it's at least NP hard. But morally, what it means is that if you attempt to solve it, it's unlikely that you would be able to solve it efficiently. So what's curious about this result is that there are heuristics that seem to work quite well in one dimension. So something like DMRG that was introduced by White in '92 and developed further by many others seems to work well on typical cases and cases of interest. However, there is no proof to date that it works. In fact, there are, easily constructed examples where the algorithms or variations of it can be forced to be driven to local minima. So there's no guarantee that the output of this algorithm will be correct. Well, you might ask how we can explain, at least for the typical cases, that this algorithm works well. So in what cases does it work well? And well, if it doesn't, can we design another algorithm that is both efficient and will give us the correct answer with certainty? The clue for us, at least in the quantum information community, came from insights about gapped Hamiltonian systems. So what's special about, I'll explain what this means. For gapped systems, there is a common wisdom apparently in the physics community that the ground states obey what's called an area law. So what's a gapped system? A gapped Hamiltonian is one in which the first excitation energy and the ground energy differ by at least a constant. So this constant epsilon here. And what's a state with an area law? So let's say you have a state over n qubits. Imagine that you draw a cut between, let's say, the ith and the I+1th state particle, and look at the state of the first I particles. So rho I is a reduced density matrix of the first I qubits. Then a state that obeys the area law satisfies the property that no matter which cut you pick, the entropy of this reduced state is bounded by B. So if you're not familiar with entropy, you can think of it in maybe slightly more familiar terms like the Schmidt rank across this cut of the pure state being bounded also by a constant. Or if you are more familiar with tensors, then the tensor rank with your tensor factorization of the first I, tensored with the remaining, is also bounded. Now, while it was commonly accepted that ground states of local gapped 1D Hamiltonians obeyed the area law, it was only a breakthrough of Hastings in 2007 that rigorously proved this. So, so the theorem that he showed, using ideas both from coming with origins in physics and in quantum information, that the ground state, let's call it C0, of any gapped 1D local Hamiltonian obeys an area law in the sense that the entropy of the reduced state given by any cut is bounded by a constant. This constant depends on both the dimension, the local dimension of the particles, and also the energy gap. So an important consequence of this area law is the following, that there's a good approximation, psi tilde, to the ground state psi0. So this is a typo here, it should be psi0, such that the Schmidt rank or tensor rank across any cut is bounded by a polynomial in n, the number of particles. And the reason that this becomes significant is that this means that you can write the ground state, or this approximation, psi tilde, in a very special form that might be familiar to some as a matrix product state with Bond dimension at most polynomial in n. Okay, and the immediate corollary is that the problem of deciding whether the ground energy of a local Hamiltonian is, is at most a certain given threshold is in the complexity class NP. Meaning, if somebody were to give you a description of this approximation here, psi tilde, to the ground state, with the claim that the ground energy is at most so much, then you could efficiently verify that this were the case, that this is indeed the case. Okay? But this still doesn't explain how we can find such a state efficiently. The ideas underlying Hastings' result were studied by fellow computer scientists over the next 5-6 years and resulted in this beautiful algorithm by Landau, Vazirani, and Vidic that actually provably produces an approximation, a good enough approximation to the ground state of a local 1D gapped Hamiltonian. And the basic ideas behind this algorithm can be summarized like so. Their approach is basically to construct this matrix product state. That's a tensor network representation of the ground state, one qubit at a time. So you build this matrix product state like so. And an insight from, in fact, classical computation tells us that once you fix what this truncated ground state looks like at its boundary, you can find an optimal completion, so the state on the previous qubits that minimizes the energy efficiently. Not only that, once you have found this, you can improve the quality of the approximation by what's known as an approximate ground state projector. So, using these ideas, what happens at the end is that the Bond dimension or the tensor rank or the dimension of the tensors increases, and a method that was in fact also used by Hastings show that we can prune the rank or the Bond dimension across all the cuts to get still good enough approximation. All of this leads to this rigorous polynomial time algorithm for 1D gapped local Hamiltonians. So for any system of n particles arranged like so, there's an algorithm that runs in time polynomial in n, 1 over delta, where the polynomial depends on both the gap and the local dimension, such that you can find an approximation psi tilde which has sufficiently high overlap with the ground state. So since I have only maybe 1 minute left, let me do the following. I'll just skip ahead to, or maybe just state the two other problems I had in mind. One is a problem in characterizing quantum devices that you might want to build in the lab. So this is a problem of the tomography flavor. So imagine you have a device which you have constructed in some state. You had a certain target state in mind, or perhaps it's a state that is not known to you and you'd like to learn different properties of it. Formally, what that means is that you have some observables, M1, M through Mn, and, or M sub little m, and for which you would like to find the expectation values trace rho mi. Okay, and you would like to do so within some additive error. Question is, well, how many times do you need to produce a state, and what kind of measurements do you need to make in order to be able to do this efficiently? And there are straightforward methods to do this. The most straightforward method requires something like m log m over epsilon squared state preparation. So the number of times you need to, prepare your device in the same way, identically every time, and then make a measurement is something like this. And what's surprising about this is that if the observables were commuting, so if you had a classical system, you could have done it with many fewer state preparations, or many fewer measurements, in fact, exponentially fewer. The second straightforward solution is also quite exorbitant. It takes something like d squared over epsilon squared measurements, and in fact, these measurements can be computationally very expensive, and so the question is whether more efficient procedures exist. And turns out that some ideas from classical learning theory can be brought to bear on this problem, and this was done by Scott Aronson in 2019. I'll skip over the exact method, but the upshot is that you can do this in dramatically fewer number of state preparations. So preparations and measurements that are polylogarithmic in both the number of observables and the dimension, with an inverse polynomial dependence on the error. And there have been many later improvements. So here's an example where ideas from classical learning theory could be used to improve the kinds of experiments that we design in the labs. It's saying 0. How much time do I have? Oh, -3 is, I'm at 43 minutes. Okay.
Yeah. So maybe if there are questions from the audience, let's take them, and then I'll ask you the question which will allow you to continue. Yeah. Yeah.
Thanks. It was very useful, very nice. So this algorithm by Landau, Vazirani, Bidic, does that suggest any generalization to other graphs, not one-dimensional graphs?
Right, so that's, I think, one of the biggest open problems in that field of work. In fact, we don't even know of an area law in 2D systems.
Suppose I grant you that.
Even with an area law, we don't know how to, we don't have efficient representations that, even with, an area law of 2D systems that we can work with.
So does it, if I think about a tree-like graph, does that help?
Right, something like, there are problems. Tree-like graph maybe, actually. Tree-like graph maybe. I'll have to think about it. Even though, maybe actually, yes.
Any other questions? Okay, I'm very curious to know what else you wanted to say.
Okay, so the final vignette was to the Tsirelson problem. And maybe I will, let's see, I just want to be able to state the problem. So you may all be familiar with Bell tests, and especially the CHSH game, which mathematically you can formulate like this. You have two players, A and B, that potentially share entanglement. There's a referee, which I'm calling V, who picks questions at random, X and Y, and poses them to, one to each player, A and B. And the players are supposed to do a local measurement on their part of this shared state phi and respond with an answer, either A for party A and B for party B. The verifier then checks whether the set of answers satisfies some properties with respect to the original questions. And in the case of the CHSH game, this particular property is just whether the two answers are different if and only if the questions were the same. Okay, so that's the property that it's checking. Now, Tsirelson asked this problem, this question, as to whether, what the correct model for these two players is. So quantum theory suggests this model of locality as follows. The state space of the two players is it models the state space of the two players as a tensor product space, HA times HB. The measurement operators that are used by A are supported only on the first space, and the ones used by B are supported on the second. And the result, so the answers, is given by this tensor product expression. But there's another model that is allowed by more nuanced models in relativistic quantum mechanics, quantum field theory, that models locality slightly differently. Here, the state space of the two parties is the same. It's a common space HAB. The players are allowed measurement operators supported on the whole space, and locality is captured by this commutation condition that the two measurement operators for any pair of inputs and potential outputs commute. So in that model, the probability that you produce, or the two players produce answers A and B, is given by this expression here. The Tsirelson problem asks whether the optimal strategy of the two players to basically win the game with the highest probability in these two models are the same for every game that you can imagine. And a stunning result from 2021 by these authors in quantum complexity theory basically resolves this problem, and implies that the tensor product model of locality is not equivalent to the commuting case. And if you want to think of it in physical terms, one can interpret it as saying that there are Bell tests. So there are certain tests of locality that you can perform that will distinguish the two models from each other. So maybe that's a good summary. I'll stop there. I had something else to say, but I think
Thank you
that
very
can
much.
wait.
Let's thank the speaker again.